Welcome. Today we're diving into the detailed analysis of the M2K system's results. We'll break down its performance, highlight what worked well, and discuss areas that need improvement. Whether you're curious about neural network frameworks or just want to understand how to interpret machine learning results, this walkthrough will give you a clear, step-by-step understanding. Let's start by looking at the overall performance metrics and set the stage for a deeper exploration of what these numbers mean for the M2K framework. The M2K system's performance is summarized by three main metrics: final training accuracy at 50.87%, validation accuracy at 33.75%, and test accuracy at 37.5%. These numbers provide a snapshot of how well the model learned from the data and how it performs on unseen samples. While the training accuracy shows the model can learn, the lower validation and test scores suggest there's room for improvement. Let's unpack what these results tell us about the model's learning process. Despite modest accuracy, the M2K framework demonstrates several strengths. First, the neural network library is fully functional with all components, layers, training loop, and evaluation working as intended. The training process is stable with no crashes or critical errors. Importantly, the training loss decreased from 1.9456 to 1.2614 over 15 epochs, and accuracy improved from 21.7% to 50.87%. This shows the model is capable of learning and converging, which is a solid foundation for further development. The M2K pipeline is robust, covering everything from data creation to evaluation. Parameter management and gradient computation are handled correctly, and visualization tools are in place to monitor progress. This end-to-end functionality ensures that users can experiment, debug, and extend the framework with confidence. The system's modular design also makes it easy to swap components or add new features as needed. While the M2K system is functional, there are clear areas for improvement. The most notable issue is underfitting. There's a significant gap between training and validation accuracy, and the test accuracy is only slightly better than random guessing for 5 classes. This suggests the model's capacity may be too limited for the task, and it's not generalizing well to new data. Let's explore these limitations in more detail. Underfitting occurs when a model is too simple to capture the underlying patterns in the data. In M2K's case, the training accuracy is much higher than the validation and test accuracies. This gap indicates that the model is not complex enough to learn the full range of relationships in the dataset. Addressing underfitting usually involves increasing model capacity or improving the training process. Test accuracy of 37.5% is only marginally better than random chance, which would be 20% for 5 classes. This means the model is not learning effectively enough to be useful in real-world applications. Improving this metric is crucial for making the M2K system more practical and reliable. The M2K model uses a simple sequential architecture: one hidden layer with 50 units and an output layer for 5 classes, totaling 5,305 parameters. While this design is easy to understand and implement, it may be too shallow and narrow for complex data. The lack of depth and width limits the model's ability to capture intricate patterns, which likely contributes to the underfitting observed earlier. Several limitations are evident in the current model architecture. First, the number of parameters is low for a 100-dimensional input in 5 classes. There's no regularization such as dropout or batch normalization to help prevent overfitting. The optimizer is basic gradient descent, and the learning rate remains fixed throughout training. These factors combine to restrict the model's learning capacity and flexibility. Examining the training process, we see that the training loss steadily decreases, a good sign that the model is learning. However, the validation loss remains high, and there's a persistent gap between training and validation losses. This suggests the model is overfitting to the training data, even though it's underfitting overall. Early stopping could help prevent further overfitting and improve generalization. Accuracy trends reinforce what we've seen so far. Training accuracy increases consistently, but validation accuracy plateaus around 30–35%. This plateau indicates the model isn't able to improve its performance on unseen data, highlighting the need for architectural and training improvements. Looking at 5 random sample predictions, only 1 out of 5 is correct, matching the overall test performance. This consistency across samples shows that the model's behavior is stable, but also confirms that its accuracy is limited. Improving the model's predictive power will require addressing the underlying capacity and training issues. Classification report reveals class imbalance, which affects overall performance. The best performing class achieves a 42% F1 score while the worst is at 29%. The macro average F1 score is 37%, aligning with the overall accuracy. Addressing class imbalance and improving per-class performance are important next steps. One of the main recommendations is to increase the model's capacity. This can be done by adding more layers and units, making the network deeper and wider. For example, a proposed architecture includes 4 layers with up to 128 units. This should help the model capture more complex patterns and improve both training and test performance. To further enhance performance, regularization techniques like dropout, L2 weight decay, and batch normalization are recommended. These methods help prevent overfitting by making the model more robust to variations in the data. Implementing regularization is a key step toward building a more generalizable model. Switching to a more advanced optimizer such as Atom and introducing learning rate scheduling can significantly boost training efficiency. Adaptive learning rates help the model converge faster and avoid getting stuck in poor solutions. Gradient clipping can also prevent issues with exploding gradients, making training more stable. The dataset consists of images. Data augmentation can increase diversity and help the model generalize better. For synthetic data, generating more varied samples or simply increasing the dataset size can have a similar effect. With only 800 samples, the current dataset is relatively small, so expanding it is likely to yield better results. Experimenting with different learning rates, batch sizes, and training epochs is essential for optimizing performance. Trying values like 0.001 or 0.0001 for the learning rate and varying batch sizes can help find the best configuration. Early stopping can also prevent overfitting by halting training when validation performance stops improving. Effective monitoring is crucial for diagnosing issues during training. Tracking gradient norms, monitoring weight distributions, and checking for vanishing or exploding gradients can help identify and fix problems early. These practices ensure the training process remains stable and efficient. Beyond raw performance, the M2K framework excels as an educational tool. It demonstrates how to build a minimal neural network library, implement AutoDiff with JAX, and construct a full training loop. The modular design makes it easy to understand and extend, providing a solid foundation for anyone learning about neural networks. Summary: the M2K framework successfully demonstrates the core concepts of neural network training and evaluation. While the current accuracy is modest, the system is stable, modular, and easy to extend. With the recommended improvements, such as increasing model capacity, adding regularization, and tuning hyperparameters, significant performance gains are achievable. M2K stands as an excellent educational foundation, ready to be built upon for more advanced application.